disappearing at 5:30 because you have better things to do. Okay, so there's quite a bit to get through here. I may skip some slides. I want to try and cover a slice of what I think is important when it comes to this idea of good unit tests, guts, good unit tests. And this kind of builds on and recaps, but takes it a little further in a few different directions. A couple of things I've said in previous years. And particularly in this talk, my motivation here is not to necessarily talk from a perspective of test-driven development, although I will cover that at the end. I'm really focused on the idea of programming with good unit tests. The idea is that TDD is a mechanism, as indeed is plain old unit testing. That's a mechanism, and defect-driven testing, these are all vehicles for how you get your test, but the objective that you're trying to achieve is this idea of a good unit test. And often we conflate the two. We get really obsessed with the mechanics of how we do it. We forget what it is that we're trying to achieve. And there are lots of people who fail to adopt TDD for a number of reasons, but one of those is they're not actually sure what it is their test should be doing. And other people are busy looking at their tests thinking, well, these tests are pretty good, but how do I talk about them? They're not TDD tests, but what is it that I talk about? And it's simply this idea of differentiating the action, the process, from the objective. So I want to look at it from that point of view. Anything that is relevant here? Yes. I will mention a couple of things from 97 Things Every Programmer Should Know, but apart from that, I want to switch to something slightly different. In everybody's head, there's an idealized way of how to develop software. It looks something like this. And this is a defined problem-solving algorithm. And we see it in the small, and we see it in the large. Write down a problem. Think real hard, write down the solution. Okay, and you can do this at the microscopic level, at your desk, or you can do this in the large. Analysis, design, implementation. And this is how people approach it. They think, oh yeah, this should work. Okay, well, what are the consequences of this? Well, sometimes it turns out that your solution becomes surprisingly visible, actually. This was sent to me by somebody. So we can see what the object model looks like, and there seems to be, that's kind of interesting. So, so sometimes we get that. Sometimes the consequences are slightly different. You're not going to make an awful lot of money out of this version of the app. So we have an obvious motivation for testing things in the small. Actually, our motivation extends to far, far larger things. This is an example I often use. This is one of the most powerful launches in the world, Ariane 5. Its maiden launch was in 1996. It looked like this after 40 seconds. How much does that cost? Well, estimation about $370 US. Millions, sorry. Millions. Lots. Very big explosion. Actually, sorry, it shouldn't be called an explosion. It's a rapid unscheduled disassembly. It's a formal term, RUD. If you ever listen to any of the launch, commentary, there are references to things like anomalies. It uses some of the SpaceX stuff. We'll talk about anomalies. It's beautifully sanitized language. But there you go, rapid unscheduled disassembly. That's what it looks like. How do we make a rapid unscheduled disassembly that's worth over $1/3 billion US? Well, you write code like this. This is in Ada, or Adatran, which is, if you're a Fortran programmer, this is how you program Ada. It cleverly sidesteps any of the useful features of Ada that would have prevented this, and expands the code. Clearly this person has been paid by line of code, and we see such well-entrenched techniques, good software engineering. You want the number 32767 in your code. Do you use a name constant? No, because if you want that number in the code, you put it in the code. That's how you know it's there. Proper Fortran style. You don't trust things like constants. These are abstractions. Never trust abstractions. This is pretty hardcore. And of course, if you're going to talk about numbers, you get bored of typing the same numbers again and again, so you switch base to base 16. That makes that a little bit more interesting. Okay, if you're going to copy and paste your code, you've really got to make things slightly more exciting. And then you keep people kind of, you don't want people to really clue in too quickly. So, underscore 32, any suggestions? What might this refer to? What does this normally refer to? Could be an integer. This is actually a floating point number, so what does that refer to? What are we saying? We are set correct. It's a 64-bit floating point number, obviously, because it's got underscore 32 on the end. And this is the kind of level of quality we're talking about here. This is actually taken from a paper you can find online. It doesn't matter if you can't speak French. The title is fairly self-explanatory. Petit bug and grande boom. And what you notice here is there is this thresholding. What we're doing here is this is a saturated conversion. If a number is greater than you can put in a 16-bit solid int, then you truncate it at the maximum value. If it's less than you can put in, you truncate it at that value. Otherwise, you do a straight conversion. Okay. Turns out Ada is very, very picky about conversions. None of this laissez-faire nonsense. You want to convert a double into an int? That's fine. Even if I can't do it, I'll give you something. Yeah. And this is what we normally do with most languages. So I'm not quite happy. This is the interesting thing. Ada was built for tolerance and safety. Had this system been written in C, Ariane 5 would have sailed into water beautifully. But you'll notice it's not applied consistently. There's a conversion here that doesn't do a threshold check. There's a conversion here that does, and there's a conversion here. Red, we know what red means when people underline something, particularly associated with a large catastrophe. This is the conversion that failed. Just so you understand, BH, underscore BH, horizontal bias, vertical bias. This is a component of the velocity, it's converting velocities. And it turns out there's no check on this, there's no if else if. Because there is no way, I just want you to kind of keep these words in your head and see if you've ever heard them before. This can never ever happen. Okay, this can never happen in Ariane 4. So what's wrong with that? Well, it's Ariane 5. Yes, ladies and gentlemen, this is software use in action. It also turns out that this code is not required. Now, the thing you have to know is that Ariane 5 has a very different launch profile to Ariane 4. You normally intellectually think of space as being up, but if you're putting things into Earth orbit, you don't want to go up, you want to go along really, really fast. Space starts 100 kilometers up. It's not very far away. Okay? But you need to be travelling at about 11,000 meters per second. You don't want to waste your time going up, you want to go along. That's why all rockets, you're going to watch them launch, they will do this. They don't go up. That's kid stuff, that's Thunderbirds. What we actually care about here is that Ariane 5 is a more powerful launcher. It does a lot more of that than that. That's its value proposition. It turns out it does enough of that to overflow this conversion. It overflows around 37 seconds into flight. It turns out that this then feeds garbage data to the guidance system, and the self-destruct mechanism kicks in at 39 seconds. So that software does work. No problem. And it was actually this system that it was discovering this that actually I realised, oh, actually, rockets really do have self-destruct stuff. I always just thought that was the stuff of Star Trek, but they really do. So somebody had a successful day that day. Author of that code. Now, the other thing is, and stop me if you've heard this one before, this code wasn't actually required. It's not only that this is Ariane 4 code that has different tolerances to Ariane 5, this functionality is no longer useful in Ariane 5. It actually serves no purpose. That functionality has been moved to the ground systems. But they just kind of left it in there because, you know, what harm could it do? So, speaking of things like code and what harm could it do, this is another system, Knight Capital, who on the 1st of August 2012, okay, they didn't lose $370 million in 37 seconds, but I'm just going to say 460 million in 45 minutes. It's still pretty good. Yeah? This is what algorithmic trading means. High-speed everything. High-speed screw-ups. Okay? It's one of those things. You're trying to put the brakes on the car, but the car is going too fast, because it turns out it's got a jet engine on the back. Okay? And it's just storming through this. Now, what is interesting about this story is it operates at a slightly different scale, but actually reflects a number of similar concerns. This is described in a really good blog by Doug Savin. nightmare, a DevOps cautionary tale. Now he frames it from the perspective of DevOps, but I'm going to say something else about this. The update to the system was intended to replace old, unused code, referred to as PowerPay, functionality that Knight hadn't used in 8 years. This is dead code, again. Dead code. So far we're racking dead code about $800 million US. Okay, we're only a couple of minutes into the talk, and this is serious money we're talking. Hadn't used in 10 years, 8 years. Why code that hadn't been dead for 8 years was still present in the code base is a mystery, but that's not the point. Actually, it is. Because when you get events like this, and you read the report, the original report on Area 5, and you look at this, events like this happen because of the perfect storm. They happen because about 3 or 4 things happen together, and that's what makes them significant. And this is the consequence. 400 million share deals. Fantastic. That's great. That's what algorithm trading means. Okay, so the point here is that this tells us you want to test everything. You're testing deployment. If you're doing deployment, there is a test that you want to run from deployment. Now, I'm going to take the focus here. I'm going to focus in. I'm going to focus in on the unit test. But this is the idea of reducing the probability of that perfect storm, whilst keeping in mind, there's an awful lot of levels in the system. So we need to keep in mind there's a slight refinement to this. Check it. We're not all Nobel physicists. Check it. Write down this problem, think real hard, write down the solution, check it. But let's actually think about how we're going to check it. The style and way of thinking about it, in terms of the timing, test early, test often, test automatically. It's kind of a little mantra, it's rule of 3. Andy Hunt and Dave Thomas captured in the pragmatic program. It sort of says it very nicely. There is this idea that we want to get in there as quickly as possible, in a way that is as repeatable as possible, a way that tells us, keeps reminding us something about the system. It checks our constraints, it checks our assumptions, and it acts as a constant shepherding exercise in terms of the quality of the code, which I'll come back to later. Because this is the other interesting thing. It is easy to start looking at these episodes and think, well, we're here, the reason we're writing tests is because we're trying to catch bugs. Actually, we're not writing tests to catch bugs. We are writing tests to create a better system, which is gloriously nebulous, but still true. To create a better system. Now, a system that is better than one we might otherwise have created, I think reducing defects is a good sign. That's definitely, we would say that's a good thing. But it also turns out that reduction is not simply because we catch them. Sometimes they never get in the first place. That is an immense value. It turns out it's fiendishly difficult to measure. You can't measure directly, you have to infer it. But this observation from Michael Feathers in a rather nice blog of his a few years back, flawed theory behind unit testing. When you write unit tests, TDD style or after your development, you scrutinize, you think, and often you prevent problems without even encountering a test failure. There is this idea that the very act of trying to consider your code from another perspective, the very act of trying to reason about it, the act of putting yourself outside the fields inside your object to look at your object through its method interface rather than out from within and looking through its fields. The idea of how am I using this? How might I work this thing? That starts you thinking. It gives you a slightly more complete sense of what's going on in your code. Just simply doing that, the act of writing the text is going to give you this kind of awareness as you start considering it. And also the awareness as you write the code of how am I going to test this. That also changes. So in other words, the very act of knowing that you're going to test, even if you weren't going to test, the very act of knowing is going to change the way you look at your code. Just as if you're writing anything, if you're writing a note to yourself, you tend to write it slightly differently than if you write a note to somebody else. For a start, I tend to try and form my letters a little more carefully because I have loads of notes loads of post-its that are written in this very cleverly encrypted notation that I have yet to decipher, except that I was the person that wrote it. When I write things for other people, I'm aware of what I'm doing. If I'm not writing it through a keyboard, I'm aware of what I'm doing, and I will form my letters a little more carefully. And I noticed a few years ago, when my kids were smaller, I was like, okay, I'm really going to, none of this joined up writing stuff, I've got to write really carefully in school letters so that they can understand. So, the very act of knowing somebody else is going to read something changes your approach to it. But it does make it difficult to demonstrate that testing has reduced the bugs because they weren't in there. And there is actually a slight sense of disappointment sometimes. When you do lots of testing, you can sometimes get this sense of disappointment. I'm putting all this effort into testing, and I'm not finding any bugs. Where's my reward? Where's my dopamine hits that I get? Because there is a satisfaction when you put in a lot of work and you are rewarded. I remember particularly one day where I didn't write tests for the whole day, and I decided, I'm feeling so incredibly guilty, I'm not going to go back to the hotel until I've written some tests. And I found 2 minor bugs. I was rewarded. I was vindicated. It was right to do the test, and I got a reward. I found bugs, and I fixed them. I felt brilliant. Okay. The next day, I continued writing my code with tests interleaved with the writing of the code. And I felt vaguely okay, but it's kind of, where's my reward? I have not found anything. Yeah? So, oh look, it's green again. How exciting. Yeah? So the only failures are when you're doing the TBD style thing. In other words, the things you were expecting. I expected it to be red. Oh, it's red. Exactly as I expected. Now it should be green. Oh, it's green. Exactly as I expected. There's certain, we have to recognise human psychology plays into this. But there's another aspect here. This was observed by Alistair Coburn, who coined the phrase guts. When he observed that people were, something I noticed as well, and it still happens, very many people say TBD when they really mean I have good unit tests. In other words, your motivation is not the mechanics of how you're doing it, it's not the personal process or the team process, but you're actually focused on the objective. Ron Jeffries, who was one of the founders of Extreme Programming, tried for years to explain what this was, but we never got a catchphrase for it. And now TBD has been watered down to mean guts. And this is often very true. You find people say, well, we're trying to do TDD or we're doing TDD, and they're not doing anything like TDD, but doing some great unit testing. And that's absolutely fine. It's just the problem is they're using the wrong term to describe their approach. So let's start talking about what we mean by good unit tests. So I'm going to go slightly old school here. This is some C code. It's a function that converts integers, an array of integers, to a comma-separated variable format, one of the most common exchange formats in the world. And here is the array of things I'm going to write. This is how many elements there are in it. Here is the output buffer to which I'm going to write, and this is how much space I've got to write into. And this being C, there's all that exciting joy of what happens if you go off the end. That would be a bad thing. So maybe we want to make sure that we have this all very well defined. What happens when I pass in a null? What happens when I pass in a null here? What happens? Well, if you sit comfortably within a managed language, you're sitting there, oh, that's okay, it's all cozy. Somebody throws me an exception that says, oh, look, somebody gave reference to null. Yeah, well, we've just taken away your safety net and all your nice toys and everything. So we're gonna just play with sharp blades here. Okay? And so it'd be really nice to know that this works. Because we have the interesting question, what if I pass in an array of integers and I don't have enough buffer for it? That's kind of an interesting question. So here's the implementation. And this is written in C99. Okay? I didn't write this code this year, I wrote it a couple of years back, so I'm just checking the version. So this is written in C99, and yeah, I think it's a pretty neat implementation, and it works. And how do I know it works? You have to take that on trust. You know? This is how do we normally work with things? That code you've written, does that work? Absolutely. I believe it does. No, we're mixing two systems. There's a belief system and a knowledge system. They're not the same. Okay, you can't trade one into the other that easily. And this is a C98 implementation of exactly the same C function. And it's a little bit smaller, it's a little bit tidier, and it has exactly the same functionality. Are you sure? Absolutely, I believe that is the case. Once again, I'm not feeling so good about this. So how do we know that we can exchange one for the other? How do we know that one does the right thing? We're going to write a test. We've got a function, we're going to write a test. And our intuition tells us you have a function, you have a test. You have this kind of alignment. I have int to CSV, so I'm going to write a function. Test int CSV. And I go through and I enumerate a number of scenarios. Okay, and I do this, and I just basic raw assertions, that's the minimum. And I go through and I do all of this kind of stuff, and there's a dot, dot, dot here, which suggests this is going to run off the bottom of the screen quite some distance. Now, the problem here is that we have, although in one sense we have tried to demonstrate the code is correct, we have not, we're missing something. We're missing an act of communication. Okay, we've focused on confirmation, but we have not got communication. We have focused so strongly on the idea that I want to know if the code does the right thing, but we haven't actually told the reader what do we mean by the right thing. It turns out that our greatest challenge in a lot of code, particularly when you come to a large code base, is not does it do the right thing. What you're trying to struggle with is what is the right thing? What is this supposed to do? What is it supposed to do from the point of view of the requirements? What is it supposed to do when this piece of code calls that third-party library? What is supposed to happen? You tell me that it's correct, but I don't know what that actually means. So, if I rang my bank up and asked them, are the transactions on my bank account correct? They would say, oh, yes, absolutely. Well, thanks, that's all I wanted to know. But what does that mean? What does it mean that they are correct? So, in other words, I only say this because I got a little reminder from my bank via my phone earlier on today. Apparently they're going to charge me for something. And, is that correct? I don't know. I mean, I know they're going to do that. I'm sure they will correctly subtract the amount of money. But is it correct that they should be doing that in the first place? What is the rule that gives rise to that? Okay. If we have a test that says random anomaly causes a debit from account, then yes, absolutely, this satisfies it. But what is the rule that leads to that? That's the challenge when you go into a code base. It's not does the code work, it's what do we mean by it works? That is a far harder thing. And this fails to communicate what do we mean by it works. It might well test it all correctly, but you don't want to maintain this stuff, even at this one-screen level. So we reach for that great tool of explanation. We reach out for it, we dig in our toolbox, and what do we find? We find comments. And always keep in mind, comments are, they are there for the reader to ignore and for the compiler to ignore. We've got two audiences, nobody's interested. And there's a lack of differentiation from a visual perspective. This piece of code now, what started as a bit of a disaster is now a complete disaster. Visually, there's no space and separation. We use space and visual design concepts to draw the human eye to, I want you to notice this, we use indentation to group things together. Aha, we can still do that. Brilliant. This is beginning to look sensible. Because now we've actually got grouping. I can now see, there's different cases here, and this case does this, and this case does this. And we struggle again, and we think for a moment, I'm sure, there's a name for blocks that have names for them. What are they called? Oh yes, that's functions. Yes! I knew that I learned this somewhere. So what I'm going to do is I'm going to turn the comments into living names. In other words, names that will appear in any artifact that explores the source code. So we now have a set, this is the full set, and this now describes the behaviours much more clearly. In fact, if we just zoom in and go with the implementation, no values from null to null output writes nothing. Positive value to sufficient output writes value without a sign. This is important. It means that when we write a positive number, we don't get a plus. When we write a negative number, we do get a sign. One of the most interesting ones, where I started with, value to insufficient output writes truncated value. Now we can mess about with the names a bit, choose different terminology, extend or compress them. But that's interesting, because this tells us that it tells us which are the three possibilities. The three possibilities, if I don't give you enough output buffer, what can happen? Well, in fact, there's even four. If I don't give you enough output buffer, one of them is you're on your own, kid. That was tough, but we're now going to just overwrite the end, which is clearly not very polite, but it would be helpful to know. Alternatively, we may refrain from writing the last digit, okay? And we may say, well, I'll write all the digits that I can, but I won't write the last digit because there's not enough, or the last number, because there's not enough space to get all the digits in. Or I may say, well, if you try to run, if you don't have enough space, I won't run anything. Okay? These are a number of options. The question is not which is correct, but which is the one that we have chosen to be correct and have we communicated that. I mean, the question is which is correct, but do we know which we have decided? If we've had a discussion about it, and one person assumes that I'm actually going to not write the last value, but I've got this, then we can have a discussion and say, hey, you write truncated value. That's not what I was expecting. You just write until you can and stop. And then that's very reasonable. You've used up all the space, but I was hoping it would be a properly, fully well-formed number, because it could stop with a minus and then you have another blank. So that's kind of an interesting case. So in other words, we may say, well, that's interesting. I never thought of that. So now we have a discussion about this, and we either write another test and we change the behaviour. We write another test to clarify, or we change our minds about behaviour, and therefore we change the name. The name is a reflection of what the code does. And in fact, we can, to the point, what we realise here is we end up with this nice little trick. Function, actually, there's only one case where you're ever going to end up with a one test function for a function, and that is if the function is hard-coded to return a single value. Yeah? That's it. If you, all other times you want to use it, and usage implies that there are different cases of use. Okay? Am I putting a null in, am I not putting a null in? Am I putting enough space, am I not putting enough space? Show the reader. Don't hide it in a comment, actually make it properly first-class citizen visible. And that gives us, you can actually just rip out the underscores from the snake case and you suddenly have function signature with documentation. Brilliant. So, documentation has never been so much fun. I can execute my documentation. How cool is that? Now, the observation that Nat Price and Steve Freeman, these guys wrote a really good book, Growing Object-Oriented Software Guided by Tests. They wrote that 4 years ago, 5 years ago. And prior to that, they've been heavily involved in JMOC, and they're kind of very strongly influential in having given us what we now perceive as kind of a more mockish universe. But back in 2007, they ran a session at XP Day. Sunday I wasn't able to go, but the blurb for this is taken from the blurb for the session. The title was "Are Your Tests Really Driving Your Development?" And they focus here. Tests that are not written with their role specifications in mind can be very confusing to read. The difficulty in understanding what they're testing can greatly reduce the velocity at which a code base can be changed. And this is the idea. We're not to test. Let's say we start thinking about test as a verb. In other words, execute your expectations or requirements. This one makes a lot more sense. And this is certainly something embraced by the behaviour-driven development community. But it's also something we should think about from any test that we write. If you don't have a test from the point of view of communication, and the idea of here we're specifying what's going to do, we're not merely checking, we're actually trying to do something far more constructive than that, it gets very difficult to read. The way they ran the whole session, if I remember correctly, was something along the lines of get people in the room, there's normally enough laptops for people to pair, they gave each pair a different problem on an index card. Simple programming problem, write some code, write some tests, and then you pass your tests to another pair who are working on a different problem. But you just pass your tests. You don't pass the index card, you don't pass your code. You just pass your tests, and now it's somebody else's job to fulfill the tests with code that they have based on tests and their understanding of what's going to do. And that's really interesting when you think about that, just as a thought experiment. Throw that back on your own tests. It's like, how comfortable would I feel if somebody just gave me these test cases? It's like, not as comfortable as I hoped. There's far too much context. You're never going to communicate everything. But sometimes you think, there's a thing I should have said, or I could have said, or I could put in the text. I could reframe them ever so slightly. So, it's time to get retro. And you can tell, this is a glorious font. This is actually a book I think this book was published in the late 70s. I read it in the 80s. And it's kind of what helped me watch it. It's rather good little book. And just a very simple observation. Propositions of vehicles, stating how things are or might be. Now, a logical proposition states a thing, and it's either true or false. And it has a particular sentence structure. And the idea, indicative sentences make sense to think of as being true or being false, capable of expressing propositions. It is raining outside. It's a statement that is either true or false, but statistically in this country, I'm going to leave on true. My coffee is getting cold. That is a statement that is also has a truth value. In other words, what you're doing as a proposition is a statement you're offering people. Here is a truth about the code that I'm working on. So this actually fits the language of specification. If you're ever subjected to formal methods at any point in your life, then this all starts making sense. You'll start thinking, oh yeah, I'm actually making propositions about what is, I'm making formal statements. They're not in a kind of classic formal sense, these are just propositions rather than using a calculus or anything, but we're making statements that a human can read, and we're attaching code to them to say, well, here is a demonstration of this proposition. Okay? This is a single instance of this proposition rather than all possible instances. But I'm going to demonstrate this, and I want to communicate that. Now, this naming style has a number of benefits. So here's an example. Funny enough, I was doing this with a group earlier today, and I will start one day using this when everybody knows the leap year rule, okay? Which means I'm never going to stop because what was great is I asked, this is fairly simple. I've been using this one for a number of years. This is not the hardest problem in software development. Let's put it this way, given it's all wrapped up in the library. It's not the hardest problem, but most people have got it wrong a long time ago. IBM got it wrong, Sun got it wrong, Oracle got it wrong, Microsoft got it wrong. Pick a company, there's probably somewhere in there, either in the present or in the past, somebody wrote a leap year checkout and got it wrong. Okay? It's just enough logic to confuse people. Just enough. Okay? The challenge here is not is the logic correct? Is what do we mean by is it correct? What is the correct concept here? And when you ask most people, what is when is a year a leap year? The guy earlier on today, it was brilliant because he actually did this perfect example of what I normally get when I ask this question. He said, "Oh, it's every year divided by 4, and then he slows down, and then it's on the centuries. And is there another one? It's kind of beautiful fade out. It's confidence. Because everybody knows the 4 years, and then somebody has the 100th thing, and then there's something else, isn't there? What is that other thing? And people kind of either they stop with confidence at 100, or they come back, well, it's 200, 400, 1,000. 1,000 is actually kind of a popular option because the most recent exception to the rule was the year 2000. And as human beings, we just latch on to false significance. We love zeros. We attach great meaning to these numbers. Okay? Oh, fireworks, year 2000, seeing in the year 2000, yeah. I don't see that happening for the year 2006. I don't remember 2006 getting the same treatment. Oh, it hasn't got as many zeros in it. It's not significant. It's not divisible this way and that. Yeah, people are really excited about zeros. You kind of notice it in this country with newspapers during hot weather. Okay, most of the year they spend their time reporting, and today's temperature was this Celsius. Oh, it gets hot somewhere in the UK. Temperature almost reached 100. What? It's boiling. No, it isn't. You switch to Fahrenheit because it's got zeros. See, and then the kind of the reactionary papers that normally seem to report things in Fahrenheit, when it gets really cold, they suddenly switch to it fell below zero, sub-zero temperatures. Well, in Fahrenheit that's really, really cold, but we don't do that in this country. It's always a bit chilly, minus a single digit maybe in Celsius. But it's got zeros in it. People love this false significance, but it turns out the rule is 400. So this is the point. The challenge here is not to write the correct formula. The challenge is to know what the correct formula is, to explain to the reader. We can categorise this out. Years not divisible by 4. Years divisible by 4 but not by 100. Years divisible by 100 but not by 400. Years divisible by 400. So although in our heads we might think there are two kinds of year, leap years and non-leap years, or common years, we might think that there's actually 4 different kinds of year. There are your typical leap years, like next year, 2016, there are your typical non-leap years, like this year, and then your atypical examples of both. Okay, 2000 is an atypical leap year, given that 1900 and 2100 are atypical non-leap years. So what we've done is we've broken this out. in old testing technique, equivalence partitions, these are the 4 different categories that are all equivalent. Now, for the sake of readability, it doesn't matter if you're normally using some kind of camel case in your regular language. I'm going to get some snakes in there. Underscores, because a proposition is a sentence, and it turns out that most of your naming conventions are based on phrases, not whole sentences. You name methods perhaps after verb phrases and classes after noun phrases, and they're shorter fragments. Although I'll be talking about the problem of long fragments tomorrow afternoon at 4 o'clock. The problem is when you start stating things, it gets really quite long. Readability for camel case is about 30 characters. We do these eye tracking studies that demonstrate after that there's a bit of a drop off. People can still read them, but not as confidently. So I'm going to use spacing to indicate spacing, which is kind of obvious really. Now, how should I go about with this? Well, one technique would be to use the word should, just as I did then. Years not visible by 4 should not be leap years. This is a technique favoured and advocated by many people doing behaviour-driven development. The idea is that it kind of invites you to think about whether or not this might be the case. The problem is it's equivocal language, it's vague language, it lacks commitment. Should is a kind of weasel word, particularly in specification terms. It's just a noise word. Years not divisible by 4 should not be leap years, but you know, hey, I should finish today at 5:30, but you know, maybe I don't. The point there is that that's not a red. That's just a case of, well, there was an example that didn't fit that, but it's okay. It was expected, because that's why we use the word should. So, if you're going to talk about writing style, Sharpen White, a fairly classic book on writing style. Don't get the 4th edition, get the 3rd edition. Make definite assertions, which is good, because they were obviously writing test cases. Make definite assertions, avoid tame, colourless, hesitating, non-committal language. When a sentence is made stronger, it usually becomes shorter. This is kind of important as well. So, we're going to go for something much more definite. I tweeted this one a couple of years back. Test names should reflect outcome, not aspiration. It's not a matter of should. It doesn't make sense to see X should give Y as the result. On passing, the result is that X gives Y. What do I mean by that? If we have these numbers, we take this strong propositional naming approach. If we have these numbers, then when these pass, you see, I'm always fascinated by how green the green will be on a projector. And that's very green indeed. And so what you now have when your tests pass is you have a listing of the things that are true of your code, which is nice because they're not just tests. They are now, if we take the specification metaphor seriously, not just as a metaphor but as identity, then what we have here is this is what it does. And when one fails, and that's a very profound red. I'm going to say this as a red-green colourblind person. I'm no problem with this at all. I just wish that testing runners would use this colours as well. And here you have one that is red, that basically says, well, you know, this thing, no, not this thing. It's the contradiction of this. Years divisible by 100 but not by 400 are leap years, apparently. Okay, that's the problem. And it tells us immediately that we have what the problem is. Not necessarily the mechanics of the problem, but where it is. What is the thing that has been violated? What is the assumption of truth that is no longer held in the code? Well, this is quite important. If we go back to where we started with the test, to CSV, if that fails, what do we know? Well, we know something about that function doesn't work. Do we know what doesn't work? Well, we can figure it out by looking at the line that failed and then work backwards and try and interpret the meaning of that. But given that we don't know what it does really in detail, there's a little bit more detective work involved than is necessary. I think my favourite example of this was a company many years ago I visited that they tried out some new tests. Unfortunately, you've always got to start somewhere, so I'll never knock somebody's efforts for starting somewhere, but it's the case of what you do to improve. The tests were numbered, test 1, test 2, test 3, test 4. Now the problem is, I'm going to go back to this idea, test should be an act of communication. When tests pass, what do you know? So when test 1 passes, what do you know? Well, whatever it is that was testing is still working. So we are communicating something, but it's very, very weak bandwidth usage here. It's just like we be saying much, but we're saying so little. Whatever it was doing before, it's still doing. And when it fails, so we actually had this with test 3, because I remember we sort of did this, and they said, okay, so, yeah, we don't know what test 3 does. And see, that's a problem with your naming scheme, Kevlin. No, really it isn't. It's a problem with your knowledge of the test. In other words, my naming scheme has revealed that you have a problem. Test 3, what does it mean when it fails? It means that something that was working is no longer working. But the problem is we don't know what that something is. We don't know whether it should have been working. In fact, we have more questions than answers. Okay? So, yeah, it's great that it may fail, but you don't want to be maintaining that. You want your test to be, it's clear acts of communication.
Just to go back to it.
Yes.
Maybe it's deliberate, but isn't the last statement wrong? It's possible by forking the not be.
What, you mean it looks like I might have copy and pasted something? That would be shocking and disgraceful. Hang on. I have no idea what you're talking about. Let's just check that I've done that on there. Yep, that's revised as well. Good. Nothing like a bit of revisionism here. That's excellent. Right, have I got all that? Let's just check that. Okay. Good. Marvellous. Right. Problem or problem? Okay. This is the other thing is review. Thank you very much. So review, really helpful. You never notice problems until they're projected large sized. There was a company I used to do training courses at. They put all their people through a series of courses over a number of years. And there was a woman there who came up to me in the break and she said, I hope you don't mind, but I found some typos in the notes and stuff like that. And and I've got a list. And I said, that's brilliant, thank you. That slide has been like that for years. And that was brilliant. Until she left the company, she was my main source for review comments because she had a copy editor's eye and would just pick up the details. So here's the errata. It was brilliant. My slides were the better for it. So a test case should be just that. A test case should be a test case. In other words, it should be a single case. I stopped using the terminology test case a few years ago. But they started again when I realised that because different people use different terminology, test functions, test methods, test this, test that. And I switched back to using test case because there is something in the phrasing that is very precise. If you decide to have an equivalence, one method means one case, then it should mean one case. How many test cases do you have in your test case? Well, the answer should be one because it's singular. But in many cases, we find a case method actually holds many cases, so therefore there is a contradiction. So there's a sort of nice way of looking at that, which I think is rather useful. So, did I get this one right? Yes, and this is why this one is better. So, there is a problem that people often encounter when they start structuring their code with meaningful long names, whether they're using should or not. They end up with these really long names with very many common parts. Now, it turns out that one of the things the human brain is really good at doing is when it sees repeated things, it tunes them out. Sometimes it overcompensates. So when you start seeing lots of test cases that have very, very similar parts to them, test when the table has unique data and significant thing at the end that's different, but then you have lots of these, you start tuning them out. Yeah? It actually turns out there's good evolutionary reasons for doing this. It turns out that evolution doesn't give a monkeys as to whether or not you're writing test cases though. Sadly, that one backfires on us. So there is this issue. Also, you find that if you've got two monitors, then you find that oh look, that test name has gone off the second monitor. There's too much there. And tests are not an exception of this. We need to think, how would we normally organise anything that gets too long? We break it up. We try and factor out the commonality. So take advantage, whatever testing framework whatever language you're using. Sometimes sometimes it's built into a framework in the style of testing, which is great. In other cases, it's not. You're just using kind of regular testing framework, JUnit, NUnit, something like that. And you think, well, how can I nudge it into doing my extra description? So I've got this kind of idea. Let's fade out the language mechanics. I've used namespace and 2 class fixtures. But when we look at the naming, leap year spec, a year is a leap year, a year is not a leap year. I've just divided years into 2 categories. A year is a leap year, a year is not a leap year. It is visible by 4, but not by 400. A year is a leap year, it is visible by 400. A year is not a leap year, a year is not, and so on. So I've got this clean way of looking at it. So when we say, your test should be like a specification, what we mean is your test should be like a specification. It really is using language structure and spacing, and you're kind of co-opting the language features to do your bidding. Different languages, different frameworks, you'll co-opt different features to do this act of communication. It means you can factor out commonality and organise it. This helps a lot. You don't want to end up with a test class when you've got 200 or 300 test methods. That's unacceptable. You wouldn't accept it elsewhere. Why would it make it better just because it's got the word test in it? It just becomes difficult to read. You've got a shopping list where you find things. And you start adding to your naming conventions to help you to find things, but that actually makes it worse. Yeah? So you're sort of fighting a losing battle. If I add more, then I might be able to find more, but you lose it. It becomes sort of homeopathic. It's diluted. So there's nothing left. Now, it turns out not only was Strunk and White writing tests, but Tolstoy was writing tests as well. And Tolstoy gave us some good advice at the beginning of Anna Karenina. All happy families are alike. Each unhappy family is unhappy in its own way. What he's trying to say here is don't just test the happy day scenarios in your code. Test the failing cases. Be explicit about what you expect. If you call this method incorrectly, if you use this object in an invalid state, what are you expecting? You shouldn't do that. Yeah, but in what way should I not do it? What are you going to tell me about my this failure? So you're going to push it back to me, or what's going to happen? So if you are supposed to throw an exception, or supposed to respond in a particular way with a flag or something, then you need to say that. That's also part of your explanation to the reader. So switching language, briefly, this is C++, C++ 11. You don't need a formal testing framework. It turns out that when you've got lambdas, you can do pretty much anything. And you can just set this up. Your tests are an array of data, and your array of data has names. No underscores needed. Brilliant. It's like, get rid of that and include punctuation and all kinds of nonsense. It's fantastic. I'm going to deal with the ISBN 13 standard. Say we've got a class ISBN, or perhaps a function that yields an object, doesn't really matter at this level. ISBN constructs a temporary object based on a sequence of digits that it's given. Now, the ISBN 13 standard, International Standard Book Number, unusually for a thing that's called a number, it actually does include digits. There's lots of things that we call numbers that aren't. Could you give me the number? Could you give me your membership? Yeah, my wife asked me the other day, Kevin, what's your driving license number? And I reeled off a series of letters punctuated with numbers. It's got letters in it, it's not a number, but we call it a number, okay? Unusually, therefore, ISBN 13s do actually require all of the digits to be digits. Marvelous. So that's one point of validation. Another point is, how many digits? Well, everything's called the ISBN 13 standard because of the name. Marvelous. So, 13 digits. Are we done? No, we're not. 13 digits. There are punctuation rules, but I've simplified it. Here I'm saying no spacing, no dashes. And there is a check digit. The 13th digit is a check digit derived from the previous 12. That's where the fun comes. So, what are we doing? Well, what we're doing here is we've got a test case here. This is basically a test snap. I've got a thing here that says test validation. So I'm doing validation. Yeah, look, I'm handling the rainy day scenarios. And here's the case with 14 digits, here's the case with 12 digits, here's the case that mixes non-digits. In this case, the 6 is actually not the correct check digit for this. then I'm expecting an exception in each case. Fine, but notice that until I told you what each scenario was, would you have immediately looked at that and go, I see the problem, it's got 14 digits there. I see the problem with this one is that that check digit, because you went through the calculation in your head, you thought, right, okay, yeah, I know how to do that calculation. Exactly, of course, everybody knows this is common knowledge, you know, it's like leap year. Less so. Problem here is that the name, the whole structure is weak. Yeah, we are testing that, you know, there is validation, but test validation, that doesn't communicate anything. Validation is an implementation to realise something. What you're doing when you validate is you're saying to somebody, this is not good, I'm going to reject this. What's the behaviour that we're after? We haven't described the behaviour, we've described the implementation. Validation is the thing that we do to fulfil the behaviour. We haven't named the behaviour. Oh yeah, I see what you mean, Kevlin. You mean I've got to test that validation works? No. This is a test smell. Sometimes you get it. Sometimes people are struggling to come up because it's hard. I'm going to say naming is really hard. And sometimes you struggle. You say, well, what am I trying to say with this? I'm trying to say that this thing works. Well, yes, so I'm going to make that name. There. You just have to ask yourself, when are you going to write a test case that says this thing doesn't work? Now, I can think of a couple of cases, bug-for-bug compatibility. Yes, we need to maintain this bug that we discovered in the next release, because it turns out people rely on it. So we need to make sure that this thing continues not to work. Yeah? But apart from that case, it's just a noise word. Test validation, it works. You know. Now I might as well have written, test the CSV conversion function works. Oh, marvellous. Where's your test that it doesn't work? You wouldn't write that. It's sort of redundant. So actually that doesn't fix the problem. This does that. ISBNs with more than 13 digits are malformed. ISBNs with fewer than 13 digits are malformed. ISBNs with non-digits are malformed. ISBNs with incorrect digits, check digit are malformed. In other words, I have been painfully explicit about this. We've gone all the way from comments through to names, through to actual proper living labels, entries in a table. This is, by the way, once you start down the table-driven route, it's really big fix. But there's that idea, that simple idea. I'm really trying to communicate to the reader. I have no issues with the fact that I've just got a bunch of one-liners. That's absolutely fine. I have no issues with that whatsoever. And sometimes there's an instinct, particularly when you see people, frameworks that take you away from the traditional method and function way of thinking can sometimes be very helpful. Because when you're thinking methods and functions, you're thinking methods and functions. And you think, I could put those together in one. Well, no, I don't want you to do that. I want you to describe these, the purpose of partitioning these things is not the traditional purpose that you partition things. So, validation is not behaviour, it's what you're after is the consequence of validation. Focus on why do we have validation here? What is the reason? Well, I'm trying to get rid of something, I'm trying to disallow something. What is that thing? Each unhappy family is unhappy in its own way. Be specific about it. So when we take all of this up to the class level, I may have a set of individual methods. And we may say, well, look, I've got tests. This is where we end up with IDEs and things. So you say, right, I'd like to test this class. Or let me start. It looks like you're trying to test this class. Would you like me to generate some stubs for you? Oh, yes, please. Or no, would you like? No, the offer is a little broader. It's only, would you like me to generate some tests for you? Well, that'd be fantastic. And then it goes ahead and generates stubs. So I've got to do all the work myself. And then it generates one test case for each method. It turns out that this kind of code generation is almost entirely useless. In fact, it's probably some of the worst code generation ever. You don't want this. It's just doing the wrong thing more automatically. So my favourite little example, recently used this. I'm going to take this through to a slightly different rendering than I've given in the previous series. I put in a construct. I don't care about other methods on this. I'm just going to be really simple. It holds strings. It's like your recently opened files menu. The idea is the most recent addition goes to the head, element 0. So it's stack-like in that sense, but it's also like a set. If I reinsert an item that is already there, it moves to the head rather than appearing twice, just as when you reopen a file in a recently use files list, you don't get it occurring twice in the menu, it moves. So that's a nice little logic there, a bit like a set, a bit like a stack. Just got a count property, an indexer, and an add method, plus the constructor. Now, if we do a one-for-one, we end up with this, and we rapidly discover we've got a problem. How do you test the constructor works? Well, I construct an object, okay, and then I have to ask a question. I presume it's going to be empty when I create it. So that means I'm going to call the count property. So I go to the count. I'm now going to test the count property. And I'm going to get it, whereupon it will return 0. But we already knew that. So maybe we need to show the count is not hard-coded to return 0. So we decide, I'm going to call add in here. And then we're going to go and do the indexer. How do I demonstrate that indexing works? Well, I have to put stuff in it. I'm going to use add. By the time we get to add, we've actually tested most of add. Except for the behaviour that is specific to adding duplicates and see what happens with those. So this gets to carry the weight of showing what happens when you do duplicates. Now, the problem is that all the behaviour, this is not much better than test 1, test 2, test 3, test 4. Because each of the behaviours is kind of scattered around. You still have to hunt for it. And if you make this a little bit bigger, say, a slightly more sizable collection interface, 20 to 30 methods, then suddenly your behaviour is kind of randomly scattered. It's kind of like, pin the behaviour on the donkey. It could end up anywhere. Where am I testing that? I don't know. Somewhere between opening curly and closing curly. Well, thank you for your help. We're not wild about this. Let's try a different approach. This isn't going to work. It's not even just that there's usage of methods, and this is the whole idea. We're focusing on usage. We're not asking the question of, is this method correct? We're going to reframe this, and rephrase this is, how are you using this thing? What is your usage? Can you explain your usage? And your usage cut across the interface of that object, and indeed other objects. We'll get to that in a bit. So you're going to end up with something that's not a one-to-one relationship. It's going to look very, very different. If I use the style I was using before, and nesting, then we end up with something like this. There's a number of different ways of doing this, I'm just showing you one. Intriguingly enough, it's not my favourite approach, but this one works. A new list is empty. An empty list contains a single addition. An empty list contains unique additions in stack order. A non-empty list is unchanged when head item is re-added. A non-empty list moves non-head item to head when it is re-added. Any list rejects addition of no items. Any list rejects indexing past its end. Any list rejects negative indexing. So I've got this kind of series of structured statements about what it is to do. And if all these turn green, then that's what it does. If any of them turns red, well, that's a thing that it doesn't do. So you have a very clear definition of what's going on. So this is kind of nicely summed up by Jared Soros in 97 Things Every Program Should Know. Now, Jared wrote this rather comprehensive book, X-Unit Test Patterns. It's about 1,000 pages long. Everything you ever wanted to know, and were afraid to ask, or didn't even know to ask. Pretty big, but I managed to get it down to 2 pages for this. Write Test for People. It's a very simple title, but surprisingly precise and appropriate. Who should you be writing the test for? For the person trying to understand your code. And notice what he says. Notice what he doesn't say. He does not say for the person trying to understand your tests. You're writing this for the person trying to understand your code. Good tests act as documentation for the test. They describe how it works. Not the internal mechanics, they describe how it works in a logical sense. They describe the conceptual model that you want the user to hold. Okay? This is very much like, if you think about it from sort of user experience point of view, except that now we're talking about programmers, are the users in this case, program experience. The user experience, you normally want to put a mental model into, conceptual model into somebody's mind, so they have a kind of a working model of how something works. If I press this, if I swipe that, then this works like this way. There's a logical sympathy to how everything fits together. It may not be reflected in the code, but that's what we mean by it works. It works from the outside perspective. That's what we're trying to communicate, not the internal mechanics. Each usage scenario of the test describes the context, starting point, or preconditions that must be satisfied. They illustrate how the software is invoked and they describe the expected result the person wishes to be verified. Now, what's important, this is not just, we're so used to bullet lists in the 21st century. Your eyes read past them. You don't even know, oh, another word this. You don't even notice this. I noticed this with my kids, you know, 9 and 13, and it's cases like, they can read bullet lists, they know what bullet lists are, they see bullet lists all the time. I didn't see bullet lists when I was 9. I had no idea what that meant. It's just not the way of the world back then. So you get really used to them. You forget there might be occasionally clever significance behind it. And there is. There's 3 of them. Whoa. 3 keeps turning up like a magic number. Actually, there's specifically 3 here. When people describe this, then when we talk about the 3 A's, arrange, act, assert. Arrange what you're going to do, act on it, and then assert the things that should be true. The same thing from a different angle and BED terminology, which I really rather like in this case. Given, when, then. If you go back to classic use case terminology, the precondition, the trigger, the post-condition, these little triples keep turning up everywhere. If you go back to formal methods, telling laws, triples, these are exactly the same things. It's like, wow, it's a grand unification moment. It's not coincidental. That's the point. There's a little narrative here. You're trying to convey this to the reader. And that gives us a hint as to the structure. So this is my travel plan for this week. It's very easy to do data-driven tests. London, Brighton, Rome. So, retains a single edition. I'm going to just create a new recent use list. I'm going to add something to it. I'm going to demonstrate there's one thing in there, and it's the thing that I put in there. Given, when, then. You may even choose. I'm not a big fan of comments, but at this point I'm going to say actually, given that otherwise your code tends to look quite flat against the margin, sometimes this is a useful learning discipline. I've normally put blank lines, very least blank lines, but actually putting given, when, then comments actually above these to break it up forces people into thinking about, well, hang on, I feel the need to put an assertion in the given bit. Should I be doing that? Am I just retesting something that we already know to be true, or am I missing a test case? So it's kind of a little nudge to help me think, why is it that I want to put an assertion halfway through? You know, is that I'm actually testing a different thing, so maybe I should factor out a different test. So that kind of discipline, that spatial discipline, is very helpful. But the example I've chosen here is intentional, because it also exhibits another thing. I've got 2 assertions here. So when you come across, this rule kind of keeps popping up all over the internet every now and then. Then you come across the rule, you should only have 1 assertion for a test case. Has anybody seen that one at all? Yeah, I was going to say Mark's hands, yeah. Yeah, it kind of keeps popping up, and like whack-a-mole. Really damn thing. There is half a truth to it. The problem is that that's not the half that people see. So I'm not picking on this person's blog. It's just that this person's blog actually illustrates this representative, and Roy Osheroff actually answered on this. One of the things that Roy Osheroff warns against is multiple asserts in unit tests. So we can blame Roy for this, okay? And we see this kind of popping up elsewhere. Proper unit tests should fail for exactly one reason. That's why you should be using 1 assert per unit test. You see, I half agree with it. I agree with the first half of the sentence, just not the second. Yes, proper unit tests should fail for exactly one reason. But that's not the same as saying the unit test should have a single assert, a syntactic assert. Because what we're dealing with is a very simple logical idea. So I've got a glass there. This is so you can treat this like a container. It's a new container. It is empty. I'm going to take a thing, I'm going to put a thing in there. Now, tell me about what I've just done. Well, there's a thing in there. Okay, we're done, test passed. No, wait a minute. We're holding back on the reader. We've failed to explain to the reader one of the most important things. It's not just there's one thing in there, it's the thing I put in there. That's really important. This is what we call a conservation rule. Okay? I put a thing in there, and there is the thing that I put in there and nothing else. That is one statement. That is one logical assertion. It's not one syntactic assertion. What I'm actually saying is there's one thing, the count of things in there is 1, and the one thing that I put in there is the same as the thing whatever. but I've had to express it in the language. So there's a confusion here between the concept. There is one concept. Don't spread it over two test cases. That's depriving the reader of an opportunity to realise that there is one idea here. It's not a coincidence. These are not orthogonal independent qualities. It's a true rule. And the idea of counting assertions is a very brittle concept. Let's just imagine that in the ... I've got some code that I want tested. So my itinerary for the week, I'm expecting London, Brighton, Rome. So I'm going to write a test case for this. So this is the test case. Here is my one assertion. Assert R equal expected itinerary. Okay, we're done. Excellent. Yeah, but I can replace that. I mean, this is slightly perverse, but I want to prove the point. I can replace that. What's actually being asserted here? Are we asserting one thing? Well, we're asserting that itinerary is not null. We are asserting that it has three elements to it. We're asserting that the three elements are London, Brighton, Rome. We're also asserting that none of this throws an exception. We're asserting 6 things. Oh my God, we have to break out 6 different test cases. That's okay. The point here is that counting language or framework assertions is a very, very brittle way of going about it. So we need to be very careful with this. Another observation that I made last year, when having this discussion with somebody, if you're using a mocking framework, any test with more than one expectation is a test with more than one assertion. And so we say, oh yeah, we follow the one assert rule. And there's this kind of, there's this description of a mock where we're expecting this, expecting that, expecting the other. But it's okay, it's only one mock thing. So we don't use the word assert, we use the word expectation. So that's a nice language lawyer trick. Yeah, but I used it earlier. The expectation is an assertion about something that you're expecting. We actually see it elsewhere. So this is the language of JMOC, for example. It says expectations in the plural. We're going to assert a number of things about our interactions. This is an important point, every single piece of mocking code that we overwrite can be replaced with a non-mocking version. Okay, you can use a test that's fine, and then do assertions afterwards, and you'll find you end up with more than one assertion. And I'm just saying, be cool with that, because it's fine, it's still one logical set of interactions, it's one idea that you're testing. It has to manifest itself in a number of individual different statements. We use the word expected as well elsewhere, so there's J, expected is used to say, hey look, an assertion with an exception is thrown. So yeah, expected is used to mean assertion. Expectation is used to mean assertion. But actually what Roy actually says, and he responded on that rather nicely, my guideline is usually that you test one logical concept test. It is the concept. Don't get hung up on the syntax. Now, often you will find there is a nice one-to-one relationship, and you should find that many of your test cases do indeed end up with one assertion. And that if you end up with lots of test cases that have more than one assertion, you should be a little suspicious. Okay? And that's fine. But that's not a driver. That's not a way of organising your test. Oh, I've got 2 assertions, split it into 2 test cases. That's a call for you to question, is it one idea or is it not? And you can tell very quickly if your naming is good, because your naming represents an idea. Sometimes you have to decompose the idea into more than one syntactic assert. So this ultimately tells us this idea of one concept. So this is the Japanese translation of most things. So I put that here for visual variety, and also because it's a beautiful example of production values. If you are going to destroy trees in order to produce paperback books, then this is how you do it. Okay, it's got a dust sheet, it's got the highest quality paper, they don't follow the standard O'Reilly template, and it's got this glorious mix of kanji, kanas and romaji. It just looks beautiful. I have no idea what it says, but it looks beautiful. And it's a really good shade they've chosen for the cover. It's just really nice. Now, translated back into English. Robert Martin points out this is a very simple idea. One of the most foundational principles of good design is gather together those things that change for the same reason and separate those things that change for different reasons. The principle is often known as the single responsibility principle, or SRP. It's a little bit of a misnomer because it's actually what actually being described here is a single reason for change, which is not the same as a responsibility. It's often coincident, but it's not identical to. But in short, says that a subsystem, module, class, or even a function, I'm going to add in, or a test, should not have more than one reason to change. And as a principle of cohesion, this makes an awful lot of sense. We can see this further reflected when we talk about cohesion. Glenn Vanderberg has his rather good blog. And if you've ever struggled with the concept of cohesion, I'm going to say coupling is a really easy concept to relate to. And it's a very physical concept, and I'm not being lewd in any way, shape or form. Coupling is a physical concept in the sense you can experience it in your code base. You can experience, we understand what high coupling means. Okay? High coupling means that every time I change this, there's a ripple effect of change going out across the system. It increases my build times. High coupling means high build times. It means a large locus of change. In other words, you can actually experience what it means for a system to be highly coupled. You can sit there looking at your watch, experiencing what it means. You can sit there, oh yeah, hot server. Yeah, you can count the joules of energy being used as a consequence of a high coupling. Cohesion doesn't have this kind of physical manifestation. It's a little more intellectual. And you know, if you've never struggled with that, just say Google Glenn Vanderberg cohesion. Yes, I am feeling lucky. Thank you very much, because that will take you straight there. It's a very well written blog, and you know, I'm glad you wrote it because I keep directing people to it. This is something I find people sometimes struggle with because it seems very abstract compared to something like coupling, which has a very strong, immediate physical sense. And he relates it to this idea of cohesion. It's cognated with the word coherent. We refer to a sound line of reasoning, for example, as coherent. These thoughts fit; they go together. They relate to each other. This is exactly the characteristic of a class that makes it coherent. The pieces all seem to be related, they seem to belong together, it would feel somewhat unnatural to pull them apart. Such a class exhibits cohesion. Quick, a few changes. This is exactly the characteristic of a test that makes it coherent. The pieces all seem to be related, they seem to belong together, it would feel somewhat unnatural to pull them apart. Such a test exhibits cohesion. The same kind of thinking applies. Cohesion is not aligned on a per method basis, aligned around a usage and a stable outcome. Now, we can take this further. As I hinted earlier, okay, we're not going to end up with a lot of classes that have demands for recently used lists and leap years. We're normally going to involve more than one class. In fact, it just takes more than one class to demonstrate. So that's it, 2 classes. And our kind of instinct is that we may align our test cases with classes. And this is not unusual. There's actually more cases where this makes sense than perhaps a single method alignment. For example, the recently used list. I can align my tests with that because it's effectively a commodity standalone class. If it's a commodity standalone class, then it has standalone usage. The problem is that most of our code doesn't look like that. These are the leaf nodes of the system. Most of our code normally interacts with something else. So, for example, if I want to go and deal with addresses properly, let's pick up the theme, given that there was a receipt at the beginning of the slide sequence. We're printing out somebody's address, or rather showing us the code that was involved in printing it out. What does an address involve? Well, typically we classify as a house number or a name. There's a street concept. It obviously depends on the geography we're dealing with, but I'll stick with the UK. There is the idea that there is a town, city, or county, and there is a postal code which has a rule of well-formedness. Okay, so you know, it's not just a string. It actually has a rule of well-formedness. And so there is a relationship between these types. I'm not just going to pass that as a string, I will actually talk about it as a postal code. So it turns out an address relates to postal code. So one type uses another very publicly. In this interface, it's not an implementation result. It's a very public thing. If I want to get a little more excited about this, it turns out the reason that British postal codes are kind of valuable is that they have a very fine granularity. The postal code refers to about 20 to 40 houses, and hence why you get sites that say, put in your postal code, and then it'll drop down, which is your house number, and bang, you're done. Okay, so the data for that is released by the post office every now and then. So it would be really good to do a lookup here. So maybe I've got some kind of lookup service, maybe I want to test that. So I'm going to provide an interface for that. So address lookup, and I'm going to give it a postal code, and I'm going to get back a set of addresses. Okay, so let me think, what have we got here? What are we involved in? Well, there's an interface, there's an implementation class. The interface, you don't write tests for those. So that's easy. There's an implementation class. We do want to write a test for that. But there's also a postal code class, and there's address classes. So that's 3 classes being involved in this, and then there are different situations. If I'm responsible for writing all of these classes, then it's all in my code. We're actually going to find that we're going to use our code in our code, and this should be unsurprising. That's why code does what it does. You have to have some coupling in the system. The goal is not no coupling, because then it's not a system. The goal is low coupling, optimal coupling. But you still have to connect the ideas. It's the relationships that make it valuable. Which means sometimes when you're testing classes, you end up with exactly this problem. There's a usage problem. I want to use this behaviour, but that behaviour is actually going to take in 2 or 3 classes across a number of different objects. And that's absolutely fine. If you organise your test cases around usages, and sometimes the usage will correspond very clearly to something like a user story, other cases it might be more specifically scenario user story. But the idea is that you may group these, and rather than thinking about a one-to-one arrangement between test and class, what you're thinking about is, I've got a group of classes whose instances achieve some objectives. Here are those objectives, and they play out across that code. So these are not integration tests, they're still unit tests, because unless I'm going to hit the network or hit the file system, they're still within, as it were, isolated from external dependencies. But there is this idea that I'm not trying to achieve a one-to-one relationship. So what are the disadvantages of not going for a one-to-one relationship between your test class and, or your test file and your corresponding other? Well, sometimes people want this for a very simple and obvious reason. Let's just go back to where that is. They want that for a very simple and obvious reason. When you look at it in the file system, it's tiny. Okay? I've got food, and I've got food tests over here. I've got bar, and I've got bars tests. I can see that visually. There's no challenge. There's a nice traceability. There's a nice visual correspondence here. And I can also track it through the version controls. So there's a nice thing going on there, and people are reluctant to give that up. Very understandable. The problem is that you can end up with surprisingly brittle tests, and you can end up with perhaps a few more tests than you really want to write. When a class uses another class, let's actually go back to the ISBN. Let's imagine a situation where we might be using, let's imagine a book catalogue. Let's imagine putting books into the catalogue. So we've got a bunch of concepts here. We've got a catalogue, we've got books, and we've got ISBNs. Now, if I use an invalid ISBN, I will receive an exception. That seems reasonable. Now, where should the validation go? Who is it that should throw the exception? The first iteration, you might just say, you know what, ISBN is just a holder class. I'm just going to, I'll put it in the catalogue. The catalogue logic starts growing surprisingly large. I know for companies, so maybe I'll move to the book. The book should be responsible for its own validity. And that feels good. Yeah, okay, I'll do that. But at the same time, there's a class over here called ISBN, and really you should give it a job. And actually, perhaps the well-formedness of an ISBN is the logical place to put it. Now, you may have provided that solution first, as indeed what happened in this particular example earlier. But the evolution to that path, we may go through each of these 3 cases, they still result in the same behaviour. In other words, you put in an invalid ISBN, you get an exception. It doesn't matter whether validation actually happens in an ISBN object, in a book object, or in a catalogue object. It is irrelevant. It is the emergent, property of the system. I say system sounds very grand. It's an emergent property of these 3 classes. There will be an exception. Don't worry about it. You don't have to get into the micromanagement of who's throwing the exception. And what is interesting is if you write these things, if you write it at one class, one set of tests, one class, one set of tests, for each of those 3 cases is where the validation happens. You have to move the code each time. What is interesting is we achieve exactly the same functionality. So, of course, we're going to have to change our test when we change the functionality, but the functionality is the same. So I want a little bit more stability. So there's this kind of constant tug of war that we're playing, which is, I don't want my test to be so vague and so broad that everything ends up being a system level test. And therefore it's stable because it's so removed from the code. At the same time, I don't want to be so close to the code that I'm hugging it to the point of actually specifying the implementation precisely. And every slight change of the implementation that results in equivalent behavior means I end up with test trip. That's too volatile. So we don't want to be so, we don't want stability that's too vague, but at the same time we don't want precision that gives us too much volatility. And we're constantly battling it out. So I'm suggesting sometimes think of it in terms of a linear usage, organise the usage and see how the classes fit into that. There'll be a little bit of diffing and a little bit of movement, but the idea is it'll be a lot more stable. You actually end up writing fewer test cases, but still achieving the same kind of effect. So there's this whole idea that what we're doing here, we've now moved to the point where we're looking at reasoning about our code. And we're talking about the difficulty of tests. So, quoting a blog that I wrote 3 years ago, where I've been teaching this for a while, but I thought I need to put it somewhere so I can refer to it properly. Sometimes it's hard to write a test. And sometimes people say, oh, it's hard to write a test because your code sucks. That's a simple summary. I'm sure from a consultancy or a co-worker perspective, you use slightly broader, more friendly language. You know, it's you're struggling with technical debt there. I'm afraid this is the issue. It's a fancy way of saying your code sucks. But what we're really struggling with here is complexity and ignorance, or lack of knowledge. And there are two kinds of complexity and two kinds of lack of knowledge that come into play here. And it's not just your code sucks, it's not just a technical debt issue. It's actually a lot more subtle. So I'll start with the boundaries. Essential complexity. Essential complexity is the complexity that is intrinsic to whatever it is that you are doing. It's nothing really to do with your code, it's to do with your domain. And you don't really get a choice in changing it. This is not a reducible problem at that level. So, for example, the leap year is essentially quite simple, but I can't make it simple. It's in the nature of the leap year. I can't say it's every 4 years and that's it. Well, I could do if I had a time machine. And I could go back in time to the court of Pope Gregory in 1582 and I could say, don't do this. The Gregorian calendar, I know you want something named after you, and I know it sounds really cool, because you're listening to all these guys who are saying that, no, forget it, just stick with the Julian calendar, okay? If you have a time machine, actually you wouldn't bother doing that, because it was just so cool. Forget it, you win, whatever. So, the point here is the essential complexity is inherent to the problem you're working with. Yeah, if you really want ultimate date geekery, you should check out John Skeet and his stuff on Node time. John is the ultimate date time geek that I know of. It's just like if there is something about dates and times that he doesn't know, I suspect we probably don't need to know it, and it can be erased from the tablets of human knowledge. It's not worth knowing. If John's not covered it or understood it in some way, he has grappled with the complexity of time zones and daylight savings time and different calendrical systems, which have sometimes almost coin flip rationality to when they mark a month, and it's just insane. And you know what? John can't make it simpler, because that is the way of the world. It is intrinsic to the problem he is solving. So I thought I'd start with the bad news. Sometimes it's hard to test, because actually it's hard. What you're doing is intrinsically hard. It's hard to write, it's hard to test. It doesn't mean it should be hard to read. The accidental complexity. Now, this moves us into a different space. This is your code. And I mean you in the plural sense. It may not be the code that you wrote, but it's certainly the code you inherited. Okay? People often wonder, why do we call it legacy code? Well, because it's an inheritance. Yeah? Just not the one we expected. So there is this, you get this code. So collectively, it is a result of, it's a byproduct of how the system has been structured. It's down to the little details, it's down to the larger details, it's down to the fact that when I call this method, when I call this method on this object to transform this data into this data, it turns out I have to have a database connected somewhere. I don't know why I have to have a database connected somewhere, but apparently I do, because in order to use this method, it's in an object that feels that it wants to talk to that database over there, even though my task does not involve that. And so suddenly you kind of reach for the mocking framework and you fire it up, and before you know it, you're mocking mocks that return mocks that mock mocks. So, but the point there is that is feedback on the complexity of your code, and that is accidental. That's not a necessary feature. If you can imagine a different code base in which the problems you're experiencing could not happen, then it's accidental complexity. But we also have a couple of areas where it's not so obvious. It's lack of knowledge. Now you'd thought if you don't know what it is that you're writing, you'd have, you'd say, oh, I don't know what I'm doing here. I should go and talk to somebody. Actually, that's not the way the programs work. Yeah, and sometimes people look at this from a sort of enterprise perspective. Well, you're not implementing the requirements, you should know you're not implementing the requirements, and you end up creating programmer-invented behavior. Okay? This happens all the time. And it's not a bad thing. I mean, it can be a pain, but it's actually a natural side effect of what it is that qualifies somebody to be a good software developer. What do we want in people that can develop software? We want creativity, and we want the ability to solve problems. It turns out that creativity and the ability to solve problems are not things that come with an on-off switch. Okay? And then you look at something and you think, oh, I'm not really sure about this. But I know what they're doing with this protocol or with this convention or this format. It should be like this because I can see how that would be the right way of doing things. Okay? And you invent behavior. You don't even know you're doing it. It's just in the flow of the keystrokes and it's done. So what we're saying is sometimes it gets out. There is this idea that perhaps you should use that little feeling on the back of your neck. You know what? I don't really actually know what this is supposed to do. I know what it should do, but what's it supposed to do? People always like using money examples, as I did earlier on. Let's focus on this. Let's focus on my bank account I was talking about earlier. Let's use the classic bank account example, because that appears in every object-oriented system ever. So all object-oriented systems are based on bank accounts, from what I can tell. All enterprise architectures are based on pet stores. It kind of goes on like this. These are the canonical examples. So let's go back to this kind of bank account concept. Now, the bank account is kind of interesting, because what happens if I try and withdraw negative money? So I've got 200 quid in my account, and I withdraw 20 quid, that should be good. Okay, I can see what's going to happen there. I should get a 180 quid result, this is all good. If I deposit 20 quid, then I should get 200 quid, which I'm assuming that all is good. That's great. What about negative money? What if I deposit minus 20? What if I withdraw minus 20? Now occasionally I get somebody saying, oh if you withdraw a negative number, it's equivalent to a deposit. That's how you flush out mathematicians. They go like, oh it's equivalent, it's just a sign difference. No, really, in the real world, it's not a difference. It's not actually the same, it is different. Are we going to take the dog out for a walk, or is that like bringing a negative dog back from the walk? It doesn't work like that. Okay? So no, wrong. Negative's bad. Okay, so I think our instinct might fire correctly at that point. But it gets much more interesting when we say, what happens when you withdraw 0? What happens when you deposit 0? It's not quite so obvious. If you think about it, your instinct will tell you, one thing. There's a good chance the person next to you is thinking the opposite. And there's probably somebody in your row who's thinking, actually, those are both really good. Or I'm not sure. This is the problem. You can actually make a good case for each one. It's not, you cannot work from first principles for this one. You might say, 0 doesn't really mean much, but it's perfectly benign. We always allow it in our systems. Okay? 0, no. We've always disallowed that. That goes back to the 1960s. The COBOL systems always rejected that, and so we maintained it. What, did you know that? That's not a fact you could have known with basically knowledge. It's a point of ignorance. You don't necessarily know this. So the idea is that sometimes it's hard to test. It's actually to do with the functionality. It's an indication of lack of knowledge. And something sometimes it's helpful to have these little nudges that sort of tell you, go and talk to someone. Sometimes there is a lack of knowing how you should test. Okay, what are the techniques that would allow you to test? Sometimes we don't know those. Okay, sometimes we don't know them. If you hadn't come across mock objects, what are the odds that you would invent mock objects? Pretty low. Okay. If you have not come across techniques, sorry, actually I'm dealing with one client that has does a lot of image processing. One problem we have is how do you test that a processed image is correct? I've got an image, I process it, what do I do? Well, this is a bit of a problem. So what they've got at the moment is they've got an awful lot of tests. Or rather, they've got an awful lot of target images. They save all the images. They go through a process of process the image and then look at it and say, yeah, that's good. Okay, we'll keep, that's a keeper, and we'll keep that one, and we'll always check against that. So it means that their tests, actually, if you run all of their tests, it takes longer than a week. They have a lot of images. These are non-trivial images, they have loads of these. And do you know what the really interesting property of this style of testing is? It's insanely brittle. Because when you improve your image processing, and you're doing a pixel for pixel match, hey, guess what? All our tests have failed. Why have our tests failed? Because we have a better algorithm. Okay, you want your test, a good unit test should, I mean it sounds really obvious, but a good unit test should pass when the code is good, and it should fail when the code is not good. It should not fail when the code is not only good, but better. In other words, we have been too precise. So it turns out that this is a non-trivial problem. Your challenge here is you have a lack of testing know-how. It turns out you have to get slightly smart about the image that you're dealing with. You have to start looking at general properties about the image and say, well, this would show this level of contrast, this sharpness, this. You have to start looking at the qualities that would tell you, you know what, this is good. You might not be able to eliminate all of the specific tests, but the idea is you have to be quite ingenious. You probably spend an awful lot of time trying to figure out how to do this and the code to support it. But that's the reason you'll find it difficult. It's not difficult because you have scruffy code. It's not difficult because you don't know what to do, in other words, what the outcome is. It's difficult because you don't know how to describe it in testing terms. So be a little suspicious when people say, oh yeah, the reason you're struggling with the test is this. It may be that, but it may not be. I like to give you more than one menu choice on this one. Now, those ringing bells seem like a perfect place to stop. Tony Gore, I only found this quite recently. I'm not quite good with the quotes, but I found it quite recently. Turns out he, as I'm following notes, pretty much everything that we get very excited about in 2015 was done last century, and probably quite a long way into last century, long way back into last century. The real value of tests is not that they detect bugs in the code, but that they detect inadequacies in the methods, concentration, and skills of those who design and produce the code. This is not a blame statement. It is simply a useful point of feedback. In other words, I want good unit tests because the very process of having to create those, whether I treat those in a TUV style or not, the very process of trying to do that informs an awful lot more than just the bug codes. It actually frames the way that you think and how you approach the code and the things you are saying versus the things you want to say. Okay, and on that note, thank you very much.